So the atomic number will be the same for all these isotopes of hydrogen. So 1, 1, and 1. The mass number will differ because these isotopes have a different number of neutrons. So if the number of protons are the same but the number of neutrons differ, the mass number, not the atomic number, will be affected. So hydrogen, the most abundant form of hydrogen, has an atomic number of 1 and a mass number of 1. So the number of protons it has, 1 proton, 1 electron. How many neutrons? Well, remember that the mass number is the sum of the protons and neutrons. And here, the mass number is equal to 1. So that must mean that in hydrogen, there are 0 neutrons. Now hydrogen 2, this is an isotope of hydrogen, meaning it has a different number of neutrons and also a different mass number. So when you see element names written like this, where it's the name of the element followed by a number, this number is the mass number. So that, like I said, that number never, ever, 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 ever comes from the periodic table. So hydrogen 2 is an isotope of hydrogen, also referred to as deuterium. There are a lot of experiments that are where deuterium is used. A lot of biological pathways have been determined using deuterium. Very useful. At any rate, the mass number is going to be 2. The number of protons is 1, just like the hydrogen above. The number of electrons will be 1 as well. Now, the number of neutrons. Remember that the mass number is the protons plus the neutrons. So we know that we have 1 proton. We must have 1 neutron here in hydrogen 2, also known as deuterium. Now, hydrogen 3 is also referred to as tritium. Has an atomic number of 1, so that means it must have 1 proton and 1 electron. The mass number is given. It's 3. Now the mass number is the sum of the protons plus the neutrons. So we know we have 1 proton. That must mean we have 2 neutrons. So in addition to coming across isotopes written by their name and then a number listed after it. So remember that this number here is the mass number. Carbon-14 is a useful isotope for determining the age of items. So we'll talk about that. It has to do with radioactivity. We'll talk about that a little bit later in Unit 1. Another abbreviation you'll come across is where you have the element symbol. So I'll do this carbon-14 example. You have the element symbol, which for carbon is C, and then the mass number is written in the upper left. So for this isotope it was 14, and then the atomic number is written below the mass number. So the atomic number for carbon, if you look at your periodic table, the atomic number is that number in blue. So carbon is 6. So this is an abbreviation that you'll come across in Chapter 3, where we discuss radioactivity. So uranium-235 is commonly used in nuclear reactors. How would you write its abbreviation? Now, if you look on the periodic table, uranium is, it's in that island, so it's in the inner transition metals. It's right here. So uranium has an atomic number of 92. So 92, and then the mass number I've given you is 235. So be familiar with this abbreviation for elements. Like I said, we'll see this in nuclear chemistry. Very, very useful. Now, I've kind of referred to this before. On the periodic table, these little numbers in red, all of these, that is the atomic weight. Now, atomic weight is different than the mass number, so you have to be really careful. So naturally occurring elements are mixtures of isotopes, meaning that you have, in hydrogen, you might have hydrogen 1 that just has 1 neutron and has a mass number of 1. You might have some hydrogen 2 and some hydrogen 3, but a much smaller percentage. So most naturally occurring elements are a mixture of isotopes. Atomic weight represents the average mass of this mixture of isotopes. So if you look on the periodic table, hydrogen's atomic weight on the periodic table is a little bit greater than 1. So So 1.00794. So 1.00794. And like I mentioned earlier, that's because naturally occurring elements are a mixture of isotopes. So there's a large percentage of hydrogen 1. Let's say, I'm just going to make up these numbers, you can look them up. Let's say you have 95% of hydrogen 1, 2% of hydrogen 2, and 3% of hydrogen 3. So that average weight is the atomic weight. The mass number doesn't take into consideration isotopes. So our mass numbers are always whole numbers. So never, ever, 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 ever pull the atomic weight for the mass number in these tables. So be careful with that. So on the next page, I want you to fill out this table. And don't use the atomic weight. Make sure you remember that the mass number is the sum of the protons and the neutrons. Okay, so hopefully you came up with the same numbers that I did. The first isotope is boron. Atomic number is 5, mass number is 12, electrons are 5. Second isotope is oxygen. Atomic number is 8, protons are 8, electrons are 8. Third one, phosphorus. 15 protons, 17 neutrons, 15 electrons. Fourth one is chlorine. Atomic number is 17, protons are 17, neutrons are 19. And then the last one is chlorine again. Chlorine has 17 as its atomic number, 37 is the mass number, and 17 electrons. So if you were to write this out, this one would be chlorine 36, and while this one would be chlorine 37. So chlorine 37 has one more neutron than chlorine 36. Okay, so now we're going to move on to arrangement on the periodic table. So why are the elements grouped in the way that they are? So remember that we talked about the periodic table. It has to do with the similar behavior. How can that be accounted for? So let's look at our periodic table. Let's look at group 1. If you look at lithium, sodium, and potassium, they're all in group 1, and they all have similar behavior. So how can we explain this? So I'm going to give you the mass number of these. Lithium put the mass number here. Lithium has a mass number of 7. Sodium has a mass number of 23. And potassium has a mass number of 39. Okay. So I want to see if we can figure out why these elements are in the same group. And remember group 1? What's the name of that? You guys know this from the earlier portion of this lecture. Alkali metals. Okay. So lithium, the atomic number on lithium is 3. So that means it has 3 protons and 3 electrons. The number of neutrons we can figure out by subtracting the mass number from the atomic number. So it has 4 neutrons. Okay, sodium has an atomic number of 11. So it has 11 protons and 11 electrons. And the number of neutrons it will have is 12. Potassium, the atomic number of potassium is 19. It has 19 protons, 19 electrons. 39 minus 19 gives you 20 neutrons. So you would think if these elements are grouped in the same, or arranged in the same group, that they would have something in common, that the protons would be the same, or the electrons would be the same, or the neutrons would be the same. But you can see lithium, sodium, and potassium, that are all members of the alkali metals group, have different numbers of protons, electrons, and neutrons. So that's not quite it. But it has something to do with the electrons. So, yeah. All of these electrons are different. So we have different numbers of electrons in all of these elements, yet they're in the same group. So it turns out that electrons are arranged in a certain fashion around atoms. It's not as nice and neat as you'd think. There is a certain probability that you're going to find an electron in this location. So you can think about these parking places that electrons can be placed in around the nucleus. And in shell 1, you can park 2 electrons. So you have a max of 2 electrons in shell 1. In shell 2, you have a max of 8 electrons. In shell 3, you have a max of 8 electrons. In shell 4, a max of 2 electrons. Now, if you've taken chemistry before, you might have learned this electronic configuration a little differently than we are, like the 1s2, 2s2, all that. We're not going to get into the s's and the p's and the d's and the f's. We're just going to keep it very simple. So, let's see how these alkali metals, how their electrons are arranged, and see if that explains the behavior. So, I have hydrogen. The total number of electrons in hydrogen is 1. So that means you're going to park 1 electron. You're going to park it in the lowest level first. So that's going to go in shell 1. None in shell 2, none in shell 3, none in shell 4. Now nitrogen has 7 electrons, has an atomic number of 7. So if I park the first 2 electrons in shell 1, because that's the max that shell 1 can contain, then the remaining electrons would have to be parked in shell 2, because the sum of these has to equal the total. Chlorine has an atomic number of 17. So in order to come up with the arrangement of electrons, I have to fill the shells, the lowest ones first, so 2, and I have to fill them to capacity. So shell 2 has a max of 8. So I've taken care, or I've parked 10 electrons for chlorine. That means I have 7 remaining, and those go in shell 3, and none in shell 4. And then calcium has an atomic number of 20. So 2, 8. So I've taken care of 10. I have 10 more to park. So 8 and 2 would be the arrangement of that. So this is just gives you an idea of how you park these electrons. Now let's go back to lithium, sodium, and potassium and figure out their electron arrangements. So lithium has a total of 3 electrons. So in order to come up with that electronic arrangement, we're going to park 1 electron in shell 1 and 2 electrons in shell 1 and 1 electron in shell 2. So that's the arrangement. None in 3, none in 4. Sodium has I'm just taking you guys out. Sodium has 11 electrons. And potassium has 19. Okay. So sodium, to park those electrons, I'm going to park the max that I can in shell 1, which would be 2. The max that I can in shell 2, which would be 8. So I have 10 electrons parked so far. I have 1 remaining. So 2, 8, 1. And then potassium has 19 electrons that I need to park. So 2 go in shell 1, 8 go in shell 2, 8 go in shell 3, and 1 go in shell 4. So, yeah, 19. Now, do you notice a trend with lithium, sodium, and potassium? Yes. The outer shell has 1 electron. So this gives rise to the periodic law. So the periodic law is properties repeat from one period to the next properties repeat from one period to the next. Elements in the same group have the same number of outer electrons. So that's the periodic law. Okay. Now electrons can also absorb energy. When energy is absorbed, the electrons jump to a higher shell. So let's say that sodium in its excited state, sodium excited, has an arrangement of, instead of 281, it's now shell 1, shell 2, shell 3, shell 4. Now 2 electrons are parked here, 8 electrons are parked here, and 1 electron is parked in shell 2. So this is just kind of gives you an idea that these electrons jump to higher energy levels. And then when it goes back to its ground state, when it goes back to 281, energy is given off. And this energy is in the form of electromagnetic radiation. So this radiation can be characterized by frequency and wavelength. And you probably remember this from physics, or you could have talked about this in math. But wavelength and frequency. So when I talk about wavelength, I'm talking about this. That is one wavelength. Frequency is how often these wavelengths pass. So, if you have a long wavelength, that means you have a lower frequency. So wavelength and frequency are always inversely related. So a long or a large wavelength means a lower frequency. A short wavelength means a higher frequency. So if you compare these two, you have a shorter wavelength. That means that wave is going to pass more frequently. So you have a higher frequency. Now frequency is directly related to energy. As energy increases, frequency increases. As energy decreases, frequency decreases. Now on page 13, I need to correct this in the notes, sorry about that, it's changed. Page 13 of your syllabus. This is the blue syllabus, the blue packet that I gave you the first week of classes. There is an electromagnetic spectrum given. And there's a lot of information on this electromagnetic spectrum. So if you don't have that right now, hit pause and get your blue syllabus. Okay, so on this syllabus, in the syllabus, you see the electromagnetic spectrum. A lot of information, you don't need to memorize all of this. What you need to memorize is the order in terms of energy of the different types of electromagnetic radiation. So for instance, gamma rays have the highest energy because they have the highest frequency, while low frequency radio has the lowest energy. So you need to memorize the order. So I could ask you on a quiz or an exam, X-rays have more energy or less energy than visible light? Well, since they're to the left on the chart, it's more energy than visible light. Infrared has more energy than TV. So you need to memorize the relative energies of the electromagnetic spectrum. So you don't need to memorize the numbers or how it's detected, none of that. Okay, also, I want you to hit pause now and write the electronic arrangements for the following elements. So hit pause and write that. So hopefully you came up with these electronic arrangements. So sulfur 286, silicon 284, beryllium 22, aluminum 283, and argon 288. So I want you to do your homework for the objectives that we've covered. Write down any questions that you have so that we can cover them when we next meet. And practice, practice, practice. Don't forget to learn the energy of the electromagnetic spectrum, so the relative orders. A lot of students forget that. That's on page 13 of your blue book. All right, until next time.